Hi everyone, so for today, we will be having dot product and cross product exercises. So as an overview, here are the exercises that we will be having today. Alright, so we have a total of 5 exercises. So the first one here, we are given vector A, vector B, and vector C as follows. And the first one that we have to find is the measure of the angle between vector B and vector C. Now, notice that the vector that was given its position representation is only vector A. Meanwhile, vector B and vector C, we do not know their position representations yet. So that is the first thing that we will be doing. For vector B, it is defined as the vector from P to Q, where P is the initial point and Q is the terminal point. To find the components of vector B, we will be subtracting the terminal point to the corresponding components of the initial point. So doing that, here we have already the position representation for vector B. Meanwhile, vector C is defined as follows, where we have special vectors here. Okay, we have I hat, j hat, and k hat. And if you recall, these are what we call our standard basis vectors. So for I hat, it is the vector with a 1 in its first component and 0 elsewhere. J hat, a 1 in the second component, and k hat, a 1 in the third component. So in order to find the position representation for vector C, we actually just look at the coefficients of each standard basis vector. And so here for vector C, we have -1 as the first component because that is the coefficient of our I hat here. 2 as the second component being the coefficient of j hat, and -2 as the third component being the coefficient of k hat. We already know the position representations for B and C, and so we can proceed in finding the angle measured between them. The necessary theorem that we will be using here is as follows. So recall that if we have two vectors, let theta be the angle between these two vectors. Then we have a formula for the cosine of that theta, and it is the dot product between the two vectors over the product of the individual norms of each vector. Using this formula for our vector B and vector C here, letting theta also be the angle between them, our goal here is to look for theta. Applying the formula, cosine of that theta will be equal to the dot product between the two vectors over the product of their norms. The way to find the dot product between two vectors, we will just be adding the product of the corresponding components of the vectors. So -1 times -1 is 1, -4 times 2 is -8, and 1 times -2 is -2, and we add them all. That is the dot product. Meanwhile, the norm of a vector is the square root of the sum of the squares of each component of that vector. For example, the norm of vector B here is the square root of 1, being -1 squared, plus -4 squared, 16, plus 1 squared, 1. And we do the same thing for the norm of vector C here. So simplifying, we get -9 over 9 square root of 2 or negative square root of 2 over 2. Okay, a very familiar expression for cosine. So in order to get theta, we just get the cosine inverse of that. So that our theta here is 3 pi over 4. And that is precisely the angle measured between vector B and vector C. Alright, so for our next item, we still have the same given, but this time we are to find the vector projection of vector A onto vector C. Before we answer this item, let us first recall what the vector projection is. So the vector projection of some vector B onto another vector A is another vector. So it's a vector, and it's given by this formula. Maybe to make it easier, let's try to visualize what this vector is. If we have this vector B, okay, and we have this vector A, so these are their position representations. In order to get the vector projection, it's as if you are making the tip of vector B fall onto vector A, and this falling, you want it to be in a perpendicular manner. In this case, it would be as follows. So like that, we are making the tip of B, okay, fall onto A, and then the vector projection is a vector whose terminal point will be that particular point to which the tip of B fell onto A. So that is precisely this vector right here. So I want us also to notice that the vector projection in this case is parallel to vector A, and in particular facing the same direction as vector A. This particular diagram though is only applicable when the angle between vector B and vector A is less than pi over 2. What if the angle between them is more than pi over 2? So consider this vector B and this vector A. Okay? Then here we see the angle between them is more than pi over 2. How will the vector projection look like? So in the same way, we want the tip of vector B to fall, in this case, not on vector A itself, but actually on the line containing vector A, like this. So the tip of vector B, you are making it fall on the line containing vector A in a perpendicular way. Terminal point would be that particular point onto which the tip of vector B fell onto the line containing vector A. And in this case, that's precisely this vector. And here we see that the vector projection is still parallel to vector A, but now is facing in the opposite direction as vector A. So we know what it looks like already. We go back to the formula. So one way to remember this is notice in the notation, the subscript is that vector onto which the first initial vector falls. At the same time, the vector projection is parallel to that particular vector onto which it falls. So that the vector projection should just be scalar multiple of, in this case, vector A. So to get the vector projection of A onto C, it's as if we want vector A to fall onto vector C. So we expect a vector here that is parallel to vector C, and so in the previous formula, all these A's will become vector C, meanwhile this vector B will become vector lowercase a. Yeah, we just apply the formula to get projection of vector A onto vector C. We have here the dot product between the two vectors over the square of the norm of that particular vector onto which the first vector falls. In this case, that's C. So the C is our star here. And again, as I said, it's just a scalar multiple of that particular vector to which it falls. So here it should be vector C. So just like in the previous item, we know how to get the dot product and the norm. This one is the square of the norm, so you just remove the square root because of the square and multiply to your vector C. And simplifying, we get this vector. And so we have the vector projection of vector A onto vector C. Now for our next item, we again still have the same given, but this time we are to find two unit vectors that are orthogonal to both vector A and vector C. So let's break down this vector that we want to look for. First, let's focus on it being orthogonal, and recall that a vector being orthogonal means that it is perpendicular to both vector A and vector C. And let's also recall that if we are given two vectors, then that special vector that is orthogonal or perpendicular to both of these vectors is the cross product between the two vectors, in this case vector A and vector B. So to quickly illustrate For example, this is our vector A and this is our vector B. Then the cross product between these vectors is another vector that is perpendicular or orthogonal to both vector A and to vector B. And so this is the vector that we will be looking for in order to find one vector that is orthogonal to both vector A and vector C here. So we will compute for the cross product. And if you recall, what we were taught last time on how to get the cross product is a method that resembles the discriminant. The way to write it down would be as follows. So here, okay, we see that we have like a 3 by 3 array. Okay, and let's analyze each row of this array. For the first row, see that we wrote I hat, j hat, and k hat, which are special vectors that we've already met. These are our standard basis vectors from before. So that would be the first row in our array. Next, in the second row, these are the components of our vector A here, which is the first vector in our cross product. Meanwhile, for the third row, these are the components of the second vector here, our vector C. So it's important to be mindful of the order of the rows that you write down in this array because interchanging the two rows will result to a different vector. The way to compute for the cross product would be to first maybe encircle this I hat here and cross out the corresponding column to which it belongs and also the corresponding row. We're left with this 2 by 2 array. So what we do is to get the product of this diagonal -1 times -2 minus the product of this other diagonal 3 times 2. And then the number that you will get here will be multiplied to I hat. To illustrate that, here we have -1 times -2 minus the product of 3 and take note it was placed in the first component of the resulting vector because again this number was multiplied to I hat, the standard basis vector, such that it contains a 1 in the first component and 0 elsewhere. Next, let's go to the second component. What you do is to encircle j hat this time and then cross out the corresponding column of j hat and the corresponding row of j hat. J hat is kind of different because to get the second component would be to multiply this diagonal 3 and -1 first and then minus the product of this diagonal here 2 times -2. So it's kind of tricky, but with practice you will remember that. Again, that number multiplied to j hat just means that the number will go to the second component of our resulting vector. Finally, for the third component of our cross product, what you do is to encircle k hat here and then cross out the corresponding row and column of k hat and then get the determinant of the resulting 2 by 2 array here. Yeah, so going back with j hat as well, the way to get the discriminant is like a reverse version of it because you start with the other diagonal minus the supposedly first diagonal. But for I hat and k hat, it just follows the usual way of finding the determinant. So going back, we have here for the third component 2 times 2. Alright, minus the product of this diagonal here, -1 times -1. And again, that number multiplied to k hat, that just means that the number will go to the third component of our resulting vector. So simplifying, we get this vector for the cross product. Alright, so we were able to obtain a vector that is orthogonal to both vector A and vector C. But note that besides the vector being orthogonal, we want the vector to be a unit vector. Now, what does a unit vector mean? So let's recall. A unit vector is a vector with norm 1. For us to ensure that it has norm 1, the method to do that would be to get the norm of this cross product and then divide it to each of the components of this vector. So yes, computing for the norm, we have this. Okay, so we already know how to get the norm. It is just the square root of the sum of the squares. And so we get square root of 26. And so our vector here is in fact not a unit vector yet, but to change it to become a unit vector, we just divide square root of 26 to each of its components. And so the unit vector orthogonal to both vector A and vector C is given by this vector. Now, we're almost done, but notice in our item, what we want are two unit vectors. We just have one. So where will we get the other vector? What we know so far is that the cross product between two vectors is orthogonal to the first two given vectors. We can find another vector that is orthogonal to both given vectors by just getting the vector in the opposite direction of our cross product. And recall, to just make it in the opposite direction, we will just be needing to multiply a negative sign to our vector. So in this case, the cross product between vector A and vector B is facing upwards. If we multiply a negative to the cross product, then we just get a vector that is pointing downwards. And because they are parallel, then the negative of the cross product will still have the property that it is orthogonal or perpendicular to both vector A and vector B. So we can just multiply a negative to this vector here. And so therefore, this is our first unit vector that is orthogonal to both vector A and vector C as before. And this is the negative of that vector, which is still orthogonal to both vector A and vector C. Note that this is still a unit vector because multiplying a negative sign to a vector does not change its magnitude. It just changes the direction of the vector so that we're sure that it is still a unit vector or a vector with norm 1. So we got our two vectors as desired. Alright, so now we are in the last item for this first exercise. Again, we still have the same given. And lastly, we are to find the area of the parallelogram having vector A and vector B as adjacent sides. For this case, actually, there is just a straightforward formula in looking for the area of the parallelogram having any two arbitrary vectors as its sides. And let's recall that formula. So the area of the parallelogram having sides vector A and vector B is given by the norm of the cross product between vector A and vector B. I want us to note that we are getting the norm of the cross product because recall that getting the cross product, we get another vector. But in this case, what we want is an area which is a scalar quantity. And so we expect that we should have a scalar quantity in our formula so that we indeed need to get the norm. To just quickly illustrate what the parallelogram looks like, say for example, this is our vector B and this is our vector A, these vectors being their position representations. Then the parallelogram having them as adjacent sides is given by this diagram. In this case, vector B and this side are parallel, meanwhile vector A and this side are also parallel. At the same time, coming from the properties of a parallelogram, vector B and this side will have the same length, and at the same time, that is also the case for vector A and this side. And again, the formula given to find the area of this parallelogram is the norm of their cross product. Alright, so we just use that formula in order to find the area of the parallelogram having vector A and vector B as sides. We first compute for the cross product between the two vectors, which will result to another vector, and from the formula, we get the norm afterwards. So computing for the cross product, this is already something that we know from the previous item. but just to practice it once more. So this was how we wrote it last time. The first row belongs to our special vectors, the standard basis vectors. The second row contains the components of the first vector here. Meanwhile, the third row contains the components of our second vector. And what we did last time was we encircled this standard basis vector first, I hat, and crossed out the corresponding column and row, and we got the determinant of the resulting 2 by 2 array, the result of which we multiplied to our encircled I hat here, which just means that the result will go to the first component of the resulting vector. And so here we have negative 1 times 1 minus 3 times negative 4 placed in the first component. Next one, we encircled j hat and cross out the corresponding column and row. And j hat is a little tricky because it uses kind of like the reverse version of getting the determinant. That is, we first get the product of 3 and negative 1, okay, minus 2 times 1. Again, placed in the second component of our resulting vector because the answer there is multiplied to j hat. Finally, for the third component, we encircle k hat, cross out the corresponding row and column, and get the determinant for the third component. So we have here 2 times negative 4 minus negative 1 times negative 1. Third component because the answer is multiplied to k hat. Simplifying, what we get for the cross product is this vector here. And from the formula, in order to just get the area of the parallelogram, we will just be needing to get the norm of this vector. So getting the norm, what we have is square root of 227, and that is precisely the area of our parallelogram. Don't forget the proper units, and so our final answer is square root of 227 square units. So now we proceed to the second in our exercises, which is actually very similar to the first one in the sense that there are given information to us and we are to find certain things using these given information. The difference now though is that observe we are involved with two vectors here, vector v and vector w. However, only vector v was the one given its position representation. And at the same time, with the information that we have regarding vector w, it may not be that easy to look for its position representation because what is given here regarding vector w is only its norm and its relationship with vector v. That is its dot product and its cross product. But maybe we can still make do with our given information here. So let's try to see how we can attack the different items by just using these given information that we have. So for the first one, what we want is this expression here. So we want the cross product between vector w and this vector, the result of which is still a vector. But again, as we said, we do not know the explicit position representation of vector w, and it might be difficult to actually compute for it. So maybe we can just rewrite this expression in a way that it can involve the information that we have here instead. So in order to write this, maybe let's recall the properties of the cross product. The first property to recall is that the cross product is distributive over addition, so that this expression here just becomes the cross product between AB plus the cross product between AC. The next property is that if we take the cross product between vector A and a scalar multiple of some other vector B, then it turns out that this scalar that we multiplied can go in different positions inside our cross product. This C can in fact go with vector A instead, and B is just a standalone plain vector. Or we can even first get the cross product between vector A and vector B, and then the answer to that, the vector that we will obtain from that, will be the one to be multiplied to C. So doing any of those methods just gives you the same vector. The next very special property of the cross product is that it turns out if we get the cross product of a vector with itself, then the answer becomes the zero vector. One way to remember this is to also recall that the cross product gives us a way to determine when two vectors are parallel. And that is, two vectors are parallel if and only if their cross product is equal to the zero vector. And of course, a given vector is parallel to itself, and so using this idea of the cross product, we indeed expect the zero vector as the answer to this. And finally, the last property that we will recall is that the cross product is anti-commutative. So if you recall in the first exercise, we said that the cross product is not commutative, but in particular, it is in fact anti-commutative. What does that mean? Getting the cross product of two vectors is just equal to the negative of the cross product of the interchanged places of the two vectors. So just need to multiply a negative sign to the commuted version of the cross product. Alright, so using all these properties, we can rewrite this expression so that it involves only these information for V and W. So rewriting the expression, first using this distributivity over addition of the cross product, then we can distribute our W into this sum as follows. And then for the next one, using this second property of the cross product, the scalars here, they can go out of our cross product. And so we do that as follows. And then for the first cross product here, we have the cross product between vector W and vector V, but what we are given is the cross product between vector V and vector W. But just using the anti-commutativity of the cross product, we can just easily interchange these two vectors, but just not forget the negative sign that we have to multiply. Meanwhile, for the dot product between W and itself, what we will be using is this third property of the cross product. That is the cross product of this to be equal to the zero vector. And so substituting those, we get this. Of course, multiplying 3 to the zero vector, we just still get the zero vector. So we're just almost done. Adding the zero vector to this first vector just gives you this vector here. And substituting the given that we have into this expression, we finally get what the vector is. And it is this one right here. Alright, so we proceed to the next item. Still the same given, but this time we meet a new vector where it has this certain m, which in fact we have to find, subject to certain conditions. In this case, we want the vector to satisfy that it is parallel to our given vector v here. Now, recall that there is another definition for finding out if two vectors are parallel to each other besides the cross product, and we recall it here. Two vectors, vector A and vector B, are parallel if and only if one is just a scalar multiple of the other. That is, there exists some C, a real number, such that the second vector is just equal to C times the first vector. And so we do that for our vector here and our vector V. Let us suppose that there is some C such that C times our vector V is this vector that we were given. And then expanding this C times vector V, we get this vector here, and we equate this vector to our original given vector. Equating two vectors means that we are equating their corresponding components, and so here we obtain a system of equations given by 2m equals c and 5m plus 1 equals negative c. Solving this system, we obtain just one single equation, and it is this one. Solving this single equation, therefore, we can obtain the value for m, and it is negative 1 over 7. The next one is still on that vector that we just met, but the m this time that we are to find should have the property that it is perpendicular to our vector v. So if before we use the operation cross product in determining two vectors that are parallel, let us also recall that we can use the operation dot product in determining if two vectors are perpendicular. And that is precisely what we do for the solution of this one. So again, once more, recalling, we can find out if two given vectors, say vector A and vector B, are perpendicular if and only if their dot product is equal to 0. Recall before, for two vectors being parallel, their cross product is equal to the 0 vector. This time, two vectors being perpendicular, their dot product is equal to the 0 scalar. Alright, so we just use this fact in order to know the value of m that will make this vector perpendicular to vector v. So getting the dot product between the two and equating the dot product to 0, we get this one right here. And recall again once more, the dot product is just equal to the sum of the products of the corresponding components. And so expanding this, we get this one. 1 times 2m, negative 1 times 5m plus 1, 0 times 0, just 0. Simplifying this, we get negative 3m minus 1, and we therefore just obtain a single equation in m. Solving for that, we hence get m equals negative 1 over 3. Alright, so now we are down to the last three items for this particular exercise, exercise number 2. But these three items are just very similar to the previous items that we did. For number 3, we are to find the angle measure between vector v and vector w. Again, not knowing the explicit position representation for vector w. But as a hint, that's okay. You can still find the angle measure even without it. For number 4, we are to find the vector projection of vector w onto vector v, something we've already learned as well a while ago. And finally, for number 5, we are to find the area of the triangle having vector v and vector w as adjacent sides. So these items can be solved using solutions that are very, very similar to what we did before. And so to test if you have understood our discussions a while ago, please try to do these numbers on your own. Again, because the solutions for these are similar to the previous items that we did. That is, here in number 3, finding the angle measure between these two vectors, you just let theta be the angle between them. And we learned that there is some expression equal to the cosine of that theta involving the dot product between them. So I hope you know what that is. For number 4, here we want to find the vector projection of w onto v. Be mindful of the notation and the proper way of writing the definition for this one. Here we want the vector w to fall onto vector v, and so we expect an answer that is a vector parallel to vector v. Likewise, this item is solved using some expression that involves the dot product between them. And finally, for the area of the triangle having vector v and vector w as sides, you just need to recall here the formula for the area of the parallelogram having these two vectors as sides. And once you've obtained the area for the parallelogram, then you just divide this area by 2 to get the area of the triangle. So these are already concepts that you know. So please try them on your own. And once you are done, you may check if you got the correct answers in the next slide. Good luck! Alright, so are you done? If so, here are the answers to the items above. Alright, so we're done with the second exercise and we go to the third one. So for here, we are given a vector d with these components, and our goal is to express it as a sum of two other vectors, say vector e and vector f, satisfying certain properties. One property is that the vector e should be parallel to yet another vector, 2I hat plus 3k hat. And the second property is the vector f should be perpendicular to the vector e. So maybe just to name this fourth vector, let's name it vector g. And once again, it is expressed using the standard basis vectors. And so expressing it in the usual vector notation, we just need to look at the coefficients of each standard basis vector. Here though, we can think of it having a plus 0 j hat. And so the second component is 0 and these are the other components of vector g. Maybe let's try to consider a diagram of our vectors. Say for example, this was our vector d and this is our vector g. Just a disclaimer that these are not the precise representations for these given vectors, but we are just using this as a guide for us to better visualize what is happening. So going back, say these are our vectors so far. Our goal is to look for a vector E that is parallel to our G. Now, we were able to meet a vector a while ago that is related to vector D, which is parallel to vector G. So it may not be easy to think about, but the correct guess for this special vector is that vector created by making the tip of vector D fall onto vector G in a perpendicular way. And now we see what it is. It is precisely the projection of vector D onto vector G. Again, once more, we recall that this projection is indeed parallel to vector G. And so, it satisfies this required condition for our vector E. So, perhaps, we can let the vector E to be precisely equal to the projection of vector D onto vector G. So, we were able to look for a vector for vector E. Now, what we need to find this time is vector F. Now, I want us to look at this vector right here. What if we try making it our vector F? Well, the projection of vector D onto vector G is this vector here. And our prospect for our vector F is this vector. See that if we add the two vectors, their sum is in fact this vector D. So far, our choice for vector F is quite valid because one condition that we need for vector F is that vector E, which is in this case we chose to be the projection, plus vector F should be equal to our vector D. Okay, so that is what we discovered here. The other condition for our vector f is that it should be perpendicular to our vector e. And because we constructed the vector such that we made a vector out of the perpendicular projection of D onto G, then our choice for vector f is indeed perpendicular to our vector E here, which we chose to be the projection. So just using this equation, we can solve for our vector f as follows. We take our vector f to be vector D minus the projection, which we chose to be our vector E, so that we may satisfy the desired conditions. Computing for our vector E and vector F, we thus have vector E being the projection. We already know how to compute given by this formula. And just substituting the quantities that we have here, we obtain this. And simplifying, we get this vector for vector E. Now, our construction for vector F is this one. And so we just subtract our vector D to our resulting vector E, or the projection. And so we obtain, after some manipulations, this vector F. So we were able to find our vector E and vector F as desired. Okay, so we are down to our last two exercises. And here we have our fourth exercise, which is actually my personal favorite. Here we will once again be meeting a usual figure for us, which is the parallelogram. And we will be considering the properties of a parallelogram and combine it to the known properties that we have for vectors. Alright, so let's start. Here we are to consider points A, B, and C. These are points where their coordinates are given, and we are to consider the parallelogram having segment AB and segment AC as its edges. Notice that we were only given 3 points of the parallelogram, which will turn out to be the vertices of the parallelogram, and we don't know the fourth. And actually, that is what we have to find. We want to look for the fourth vertex, say D, of our parallelogram. So first, let's approach this problem maybe through a diagram to better visualize it. So for example, this is our three-dimensional space. Let's name as 0 the origin. And let us consider the points A, B, and C as follows. Again, another disclaimer that these are not the precise representations of our points, but we just use this as a guide to attack this problem. Okay, so these are our points, and it says here that we are to consider segment AB and segment AC as edges. So let's do that. Alright, and we construct the parallelogram having these as edges as follows. So this is our parallelogram, and again, we do not know yet what the fourth vertex of our parallelogram is. So we have to know what the coordinates of point D is. Oh, I found a typo here. It should have an S. Coordinates. Okay, so of course our lesson now is on vector calculus. And what we have so far are just points. So maybe let's make our vectors appear in our diagram. Let us first consider maybe vector OC, the vector having O as its initial point and C as its terminal point. And let us then consider the vector CD, where its initial point is C, its terminal point is D, which we don't know yet. Now, looking at these two vectors, okay, notice that if we add these two vectors, the resulting vector is precisely this vector, vector OD. O its initial point and D its terminal point. Notice that knowing what the coordinates of D are is just equivalent to knowing what the position representation of vector OD is. So maybe let's focus on that goal of finding what vector OD is. And again, this vector OD is just the sum of vector OC and vector CD. So if it so happened that we know what these two vectors are, then we can know what vector OD is, and consequently, we will know what the coordinates of point D are. Okay, vector OC, we already know what it is because we will just be subtracting the components of C to the corresponding components of O. So this is a check already. But what we don't know so far is vector CD because, well, we don't know what D is. So let's try finding what vector CD is. Now, there are other points here that we haven't approached yet. So maybe let's consider the vector between them. This vector right here, vector AB, having A as its initial point and B as its terminal point. We considered this because actually it has a very special relationship with our vector CD here. What is that special relationship? Well, it comes from the properties of a parallelogram. In particular, the fact that for a parallelogram, its opposite sides are parallel from the name itself. So this side of the parallelogram and this side are parallel, and so therefore vector AB and vector CD are parallel as well. At the same time, in the way we constructed vector AB and vector CD here, they are both going in the same direction. So let's take note of that. And another useful property of a parallelogram is that its opposite sides are also of the same length. So this segment here and this segment here have the same length. So consequently, vector AB and vector CD will have the same norm or magnitude. So again, vector CD and vector AB are parallel, going in the same direction and have the same length. Recall that these are precisely the required conditions when we say that two vectors are equivalent. And so therefore, we have discovered that vector CD and vector AB are in fact equivalent vectors. Again, initially our goal was to look for vector CD here to find what vector OD is. But since vector CD is just equivalent to vector AB, then we can just go and find vector AB instead, which is now very easy to find because we already know what the coordinates of point A and point B are. Okay, so we already have our important tools to solve this problem. Again, what we know is that vector OD is the sum of these two vectors, vector OC and vector CD, and that vector CD is just equal to our vector A. Okay, so using these two equations, we first compute for vector AB to know what vector CD is, and we get this vector right here, just subtracting the corresponding coordinates of our points B and A. So we get this, and that is precisely our vector CD. And substituting this vector into our equation here, already knowing what vector OC is, which is just this in vector notation, then we can look for vector OD as follows. So we know what vector OD is, and again, this is the position representation of vector OD. So just changing this in point notation, that is already our point D. So therefore, the fourth vertex D here is this point having these as its coordinates. Okay, so we already know what the four vertices of our parallelogram are, and so it is already complete. And for the second and last item for this fourth exercise, we are to now find the area of the complete parallelogram. This is already something that we've encountered earlier, so this is just a review. So just to recall, what do we need again to find the area of the parallelogram? Well, what we need are two vectors forming adjacent sides of our parallelogram. Here, actually, in the given, we are already given adjacent sides of our parallelogram, which we just transform to become vectors, which are vector AB and vector AC. So we just need to find their position representations, and these are the tools that we will be using to find the area of the parallelogram. So in this particular parallelogram, we've already answered the question. The two vectors could be vector AB and vector AC. Note that there are other possible pairs of vectors, but this is the easiest choice because we already know what vector AB is from the previous item. What we just need now is the position representation for vector AC. So kindly compute it on your own, and then from there, find the area of the parallelogram using a formula that we already mentioned a while ago. Try this on your own and check if you will get the correct answer. What did you get? If you are done, here is the solution and answer. This is the formula that you should have used, and the answer that you should have obtained is this one. Hope you got it right. Okay, so we are finally at the last of our set of exercises. This is exercise number 5. And as a culmination of the many concepts that we have learned today, we have here a proving item. So let's see what we have to do. Here we let vector A and vector B be non-zero vectors. And what we want to prove is that the vector projection of vector A onto vector B is perpendicular to this vector obtained by subtracting vector A with the projection of vector A onto vector B. So the concept here is two vectors being perpendicular, which is something that we've encountered earlier. But to recall once more, how do we know again if two vectors are perpendicular? There is this operation between them that we use. And if you recall, that is precisely the dot product. And we know that two vectors are perpendicular if and only if their dot product is equal to the zero scalar. So this is the concept actually that we will be using to prove this item here. That is, we will be needing to show that the dot product between the projection of vector A onto vector B with this vector, vector A minus the projection, is equal to the zero scalar. To guide us, we will give some tips in proving this item. So one tip is that in proving this, we will be needing to take note of properties of the dot product. The first one that we will recall is that the dot product is distributive over subtraction. Next, similar to the cross product, if we have a scalar multiplied to some second vector and we take the dot product of that with some first vector, this scalar can in fact transfer in and out of our dot product as follows. Any of the methods will give us just the same vector. The third property that we will recall is that the dot product is in fact commutative. The dot product between vector A and vector B is just equal to the dot product between vector B and vector A. Finally, a property of the dot product is that if we get the dot product of a vector with itself, then the scalar quantity that we will obtain is precisely the square of the norm of the vector. Okay, so these are the properties that we will be recalling, which we will be needing to prove this statement right here. At the same time, of course, we are to recall the definition of the vector projection of vector A onto vector B. Be very careful in the way of writing explicitly the definition. These are, in fact, the only concepts that we need in order to prove this item. Maybe try answering this on your own. The proof for this item will be discussed in the next slide, but work on it first to test if you have indeed understood what we've discussed so far. Once you are done, you may check if your proof is correct. Good luck! So, are you done? If so, here is the proof for this item. Again, we want to prove that these two vectors are perpendicular, and showing that these two vectors are perpendicular is just equivalent to showing that the dot product between them is equal to 0. So we prove this statement in that manner. Indeed, considering the dot product of the two vectors, we first use the property that the dot product is distributive over subtraction. So we do that here. And then for the next line, just to write explicitly the definition for the vector projections, we have this. So this was just rewritten, no magic happening here. And then next, using the property of the dot product that the scalars here can move in different positions inside our dot product, we rewrite it this way. So we just leave the plain vectors involved in the dot product, and all the other scalars, we put it outside. So just to rewrite this better, let us commute the two vectors here, which is completely fine because anyway, the dot product is commutative. And then here, we are taking the dot product of vector B with itself. So it is equal to, from last time, the square of the norm of vector B. So we substitute those quantities here, and we have this. So see here in the second expression, we can in fact cancel these two. And simplifying, we just obtain this. And observe that they are just completely the same vectors now. And so therefore, their difference is just equal to 0. So indeed, the dot product between these two vectors is equal to the 0 scalar. That is, they are perpendicular vectors. And we have proven this item successfully. Okay, so that's it for our exercises today on dot product and cross product. Thank you for listening, and I hope you keep safe and healthy always. Bye!